Okay, okay. Things appear to be working. Let's share a screen. Welcome, welcome, welcome. People are arriving at Sylvania. People are arriving in the Zoom. Welcome, welcome, one and all. Let's hide my little video face from me because it's weird looking. Welcome, 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 welcome. A minute or so of free class time, spacing out. Ooh, ooh, I'm a little tired. A little tired. Last night was karaoke night. Stayed up a little late. What's that?
Finally got to do the karaoke thing.
Yep.
The first time, right?
Back to full health, able to sing. And when I got to karaoke night, there's almost nobody there. So like the 3, 4 people there singing, 2 people worked there, and the other 2 of us were just singing away for like an hour. It was fun, just taking turns. Highlights were when the bartender sang Comfortably Numb by Pink Floyd. Dean sang that one. Sounded killer. He did both a good Roger Waters and a good David Gilmour, because he's a real Pink Floyd liker. My neighbor, the other non-worker, did Betty Davis Eyes by Kim Carnes. Big hit song from when I was like 10 years old.
What's your
I try to change them up a lot, but I guess if I was gonna go to a new karaoke place where I haven't, where I could just draw into the old well of songs. Crazy Train by Ozzy Osbourne is pretty great.
They love that.
People love Crazy Train by Ozzy Osbourne.
That's so fair.
Yeah. Or if people just want to relax, you got Pictures of You by The Cure. It's a long song that feels short because it's so good.
You know, Ozzy's going back on tour with a lot of their rock bands. Like it's his final tour because he's got to retire.
Oh, Ozzy, I cannot believe he's still going. I would have thought he would have died like 2 weeks after they filmed Decline of Western Civilization Part 2, The Metal Years in 1984. He looked pretty bad in that movie. He could barely express himself. And then I couldn't believe he was still alive during the Osbournes reality TV show. But he just keeps going, and he's a creative guy, he's a thoughtful guy. Yeah, Ozzy Osbourne. He never really went fully off the rails on that crazy. Sorry, Ozzy. I know, I know. I get it, Ozzy. In any case, people are settling in. It's about a couple minutes past the hour. This is great. We got a big group here in the room at Sylvania. We got a good sized group of folks in the Zoom room, wherever the rooms you are in reality are. I hope you're warm and comfortable and have great internet connections on this rainy winter day. It is rain week in Portland, Oregon. Let's give it another few seconds while a few more folks arrive through their notification screens. During those seconds, though, think about it. Do you have any questions about recent work, things you're working on in stats class? Any questions, homework type stuff? We've learned a lot about some abstract topics lately. We got our probability distributions like random variables. That section's got some funny homework problems. We just scratched the surface on the new normal distribution last class, so I'm guessing we don't have any questions there yet. But any other probability questions on your mind that are bubbling up in your brains? If they're there, let me know in the chat if you're out there in the world or via your mic. Or if you're in the room, just shout it out. while we make our path to today's plan. Here we go. I'm heading into our D2L, bright space content. First up, I like course materials just to double check what the schedule says. Last class, I know because I looked right before class started. So if you didn't notice me peering out into the internet, I was peering back. I looked back in time and I saw that last Wednesday we started this discussion. For one, didn't finish it. Our goal today, for sure, is to finish this discussion. And we want to work on the lab that is the partner of this discussion. That's ideal. For two, well, dream world. We'd open up that discussion as well. Maybe not finish, maybe finish everything 1 hour, 2 hour, 3 hours, just 3 things, do them all for 1 hour. That would be like the perfect ideal dream world. But I don't dream like that because I never know how long things will take until I do them in reality. So we'll just start with wrapping up the discussion from last class. Then we'll work on the lab. Time permitting, we'll open up that other discussion and we'll just see how it goes. All right, I don't see any questions arising in the chat. I don't see any questiony faces or hands in here. Let's get into the new stuff or the continuing discussion of the normal distribution. Here we are. Yeah, let's go. So back into content. Hey, great. That doorbell is ringing. Lots of folks are entering the Zoom as I speak. Welcome, welcome, welcome. Right on time for our rejoining our conversation about the normal distribution. Slides from the first section of chapter 4 is where that discussion lives. Another good karaoke song, Changes by Black Sabbath. Ozzy Osbourne's really a great singer, it turns out. I never got into Black Sabbath when I was younger. I just missed him while I was getting into what I did get into. But now I know they rock. All right, blazing fast return to this discussion. Normal distribution, it is a continuous probability distribution. So it looks a heck of a lot more like the curve on the bottom left there. But even more continuous looking because it's unimodal and symmetric. Remember, in this probability distribution world, think of 100% of the probability is the area under the curve. The mean's at the center because it's perfectly symmetric. Its symbol is mu, Greek letter. Standard deviation catches about a little more than 2/3 of the area in the center there, symbolized by the symbol sigma. Oh, that's Carl Gauss, my good old, disciplinary, great, many greats grandfather. Not a personal relative, but in math, he's one of my grandpas. Love you, Carl. Supposedly he was a nice grandpa to his real life grandchildren. We talked about this amounts of area expected under a unimodal symmetric distribution last class. Looked at an example with some data. We talked about SAT scores following this curve's design of the test takers. We got a peek at how the curve looks when you change the mean or standard deviation on scale shifts, and the curve just gets, wider and shorter the bigger the standard deviation gets, because it has to have the same area under the curve every time to have that probability distribution style. Standardized normal curve is centered at 0. Standard deviation is set to 1. The units, well, they're called standard deviations by people who know what they're called. And if you're also a statistician, you would call them z-scores. That's the weird sounding name that statisticians adopted at some point in history. And it was also the topic of my teaching demonstration at my interview that got me this job. And I learned about it specifically for the interview. Bang! And when they said, how many times have you given your practice lesson in classes? I said, never. I can't lie. I just made it up for the interview. And they went, but luckily, the first choice for the job didn't take it, and now I'm here. All right, we talked about comparing scores on different scales. Here it's the SAT scale, the numbers in the hundreds to 2000s on the lower left, comparing to scores on the ACT test with scores ranging from about 6 to 36 on that test scale. We learned a little more about how the SAT, along with the ACT, are monstrous projects developed by eugenicists to harm tons of people and to propagate ongoing racism and white supremacy. Shitty idea, Mr. Brigham, but thanks for letting us know, Dr. Lunama. We looked at directly how to calculate how many standard deviations something is from its mean, so calculating z-scores. We got the formula for that on this slide. And we got a little note, z-scores are useful, especially in the world of unimodal symmetric data, or in a normal model if using a model. And that once you get out greater than 2 standard deviations from the center of the unimodal symmetric data set, or using a model like the normal curve from great-great-grandpa Gauss, yeah, you're considered an outlier in that world because it's less than a 1 in 20 chance of being more than 2 standard deviations from the center. And here's where I said, we don't have time for this one. Let's talk about this next Monday. So let's downshift back from blazing speed to get us back on the same page to safe speed, the speed limit. Let's go the speed limit in this discussion. Okay. I'm going to retitle this slide slightly. Let's retitle it Ye Old with an E. Ye Olde normal approximation for data. And let's add at the end which no one ever does now that pretty much everyone has access to powerful computing. See that? This was a really useful technique back in the days BC. That's before computers, according to historians. But nowadays, this technique is becoming anachronistic and it's a little odd. So like if you want to look at this data set here, it's heights of some people measured in inches. And the average person they measured is smaller than me, so that's cool. I feel tall in that distribution. But you can see like the chunky part of the graph is like a histogram of their data set. And then it's such a unimodal symmetric data set that they're comfortable talking about it in terms of a normal distribution of these heights. This is much like the graphs I see at the pediatrician's office about the heights of children the same age as mine when he visits the pediatrician. They vary like that. They're just much shorter because they're children instead of adults like these folks. But now, and we can see in the picture, just because they've labeled it with standard deviations, we've got the mean at 63 and a half. So here, let me go over to my buddy GeoGebra to look at this for a second. I'm heading to our links in our class page. I love that GeoGebra Classic link. It saves me typing and going to the weird GeoGebra pages if I mistype things. Love it. And then I land at the probability calculator. That's where our normal curve lives. We'll learn more about using this today. But just for this example, I want to show you, look there, there's the standard curve. It's centered at 0 with standard deviation 1. And that scale, the 0, 1, 2, 3 you see here, that is the same scale on this slide, standard units, so-called z-scores. In olden times, like say you wanted to use the normal curve to estimate how many heights are between 61 and 66 inches. That's 1 standard deviation above and below that mean value. In olden times, you'd have to convert these values, 61 and 66, over to z-scores to then use the existing technology of a table of values for areas under the curve with mean 0 and standard deviation 1. These were in statistical tables books in the back of every introductory stats book still to this day. But that's weird now because now I can just see the standard deviation here is 2.5 inches. So if I center it at the 63.5 inches here, turn on the numbers on my computer. Most people don't type a leading 0 accidentally in front of numbers. 2.5 inches like that. And I can just really, really quickly double check that I get that standard deviation right. If we go down to, what was it? From 61 to 66 inches. 61, 66. Yeah, that's if you round it off to the nearest whole percentage, 68% of that area under that smooth curve. Notice to calculate this area here to 4 decimal accuracy, I didn't even think about calculating a z-score. That would have just slowed me down. I already know the standard deviation, 2.5, and the mean, 63.5 with a rare leading 0, even though it doesn't affect the value. It looks weird. It keeps coming back too. I don't know why. Good job, GeoGebra, to remind us that most of us don't write leading zeros on numbers. But see, like that, so this first step on this slide here, this step, let me just cross it out because that's step 1 there. That is anachronistic. That's old timey. That's oldie timey. It's just for no computer days, for no computer times. So that's a step that I'm not going to expect you to mess with. I don't want you to think about calculating a z-score every single time you need to figure out a likelihood using the normal distribution. I want you to just use the mean and standard deviation and the most accurate tool you've got, which is GeoGebra. So step 2, let's go ahead and emphasize step 2 even more. Use technology to find well, we don't need corresponding, we just need the area under we don't need standard normal curve, we just need the normal curve, with correct, with correct mean and standard deviation, and we're in good shape. So the whole normal approximation piece, it's kind of weird in modern times. It's just an anachronistic, old-timey thing. I think the reason it hangs out in statistics books is if you go to like I don't know, I'm trying to think of a math department that has a particularly skewed older, and also skewed more academically conservative department. Maybe Stanford math department in California, or maybe the University of Chicago's math department and stats department in Illinois. A lot of the guys, and it's mostly guys who work in those departments who are older, they learned these techniques in the 60s, right? They're now like guys in their 20 years older than me, right? So they learned these techniques in the 60s and 70s, and they think they're really important for everyone to learn because that's how they did it. And that's how they understand it. So that's how everybody has to do it forever, even if we all have a computer in our pocket. Does that make sense, those guys' attitude? Would you say it's good or bad? Yeah, it sucks. It's a bad attitude. Things change. Technology changes. And, we have good technology now. You got the mean standard deviation. You got the technology right there. GeoGebra is our little buddy. We can quickly do these kinds of calculations just using the best tool at hand. And that's free technology that's in our pockets on the internet today. So sorry, my statistical uncles who are not as cool as Carl. But in any case, I can see how they feel. There's things I like that are old-timey too, just because I'm old-timey and I like them. That reminds me to get something old-timey set up this summer to play with. Okay, now, so, but finding areas under the standard normal curve, this skill is still good because you're still going to get asked questions sometimes about how likely it is to be within a certain number of standard deviations of the mean. These are still meaningful questions. We can always reset our mean and standard deviation as we like, but these are good little practice questions to double check that we're getting GeoGebra's probability calculator working for us. So I'm gonna just type up for notes those probability questions, z less than -1, probability z less than -1.5. Z, remember, being a standardized score. Probability z greater than 2.1. In English, that would mean the likelihood you find a value in one of these unimodal symmetric distributions that's more than 2 1/10 standard deviations above the mean. Long sentence collapsed into just a few symbols. And we can also focus on intervals, likelihoods of being between two values. So from 1 2/10 standard deviations below the mean up to 2 1/10 standard deviations above the mean. Well, what's that probability? These are pretty abstract questions, but they're really relaxing to solve and get done using our buddy GeoGebra. So let's go peek over there. If you're at home or in the room, I strongly recommend following along at least with one or two of these examples. I'll give you a direct link to the page I'm at internet-wise in the chat, but I strongly recommend starting to mess with this now as we talk about it. That way, if something doesn't work for you personally, you can say, Ralph, can you show me that one more time? Or, Ralph, where was that control? Or, Ralph, how did you get it to look in that direction? Because there's just a few, like everything with technology. When it's new, it's unfamiliar. After you've used this for 5 to 10 minutes and done 3 or 4 homework problems, it should feel familiar. Okay, so all these questions are back in the world of z-scores. So that z right there means we do need to reset the mean to 0 and deal with standard deviation 1. Z 1. Okay, and then the nice thing is the symbols less than and greater than, they align with the controls down here, right below that menu that has the normal curve selector in it. So let me just grab a pen here. This one pointing off to the, see, it's like a little bracket that kind of points off toward the left, so this is our less than. This is our little less than bracket. This one over here, this bracket, the last one on the list, points like little goo pointing out of there to the right. So greater than points to the right. So that would be the greater than one. And then when you've got two brackets like that, that point toward each other, that'll get us an interval, the area between two values. And if it's two brackets pointing away from each other, we can figure out the area like out in the two tails of the distribution, which is useful in some settings that we'll talk about in chapter 5. But the main three are maybe this one here is I can't draw that small, but yeah, the main three are the first, this one, and this one. Those are the three we use the most, especially this first set of homework problems in practice. Clean that up a little bit. Okay, so then to set these up, oh, wait a minute. Quick question. Does a calculator help you understand like how math works?
No.
Not really. It helps you get results correct when you know how to set up calculations. So calculators do not help us understand what we're doing so much as they help us do things we understand very quickly, right? Now, the trick with statistical calculations is we do so many of them using computers that it's pretty difficult as we blaze through all the concepts and ideas this quarter to kind of humanize and really understand what all these calculation results we're getting mean. So there's one sort of leftover piece from the olden days version of this process that I still think is good. let me just show you how to like go a slightly more human speed with these calculations. It involves just taking the time to draw lots of cute little bells. And most people, if you give them a pen and ask them to draw a bell, they're gonna love it. If you're not a regular bell drawer, I recommend trying it this week because it's pretty fun. So like, look at this first option here. Let me just slow this down to human speed. Probability Z is less than -1. If I've got a piece of paper near me, I'm immediately just going to draw a little bell. Doesn't have to be a perfectly symmetric, beautiful bell, just a little bell. Whenever I draw one, I always quickly note the mean. In this world, it's 0, the center of those standardized Z-scores. And I always just draw in a little standard deviation measurement. 1, goes in both directions. And then, to get into the world of calculations, I'm going to draw in, here's -1, down there on that scale. And I'm just going to fill in that little thing. And I've got a little picture in my notes now of what I want to see when I do my calculation. Yeah? Feel the humanity, feel the human speed there. See the artistic value of my little drawing? Or really its conceptual value. I'm reminding myself and learning more about how the curve works just by sketching it out. And then the analytical way it slows this down is now that's the area I want to find here in GeoGebra. But if you were just going to guess, if the little picture has 100% area under my little bell I drew, what percentage of the area did I color in there below -1, would you guess? It's the guessing that engages your analytical thinking and slows down this probability thinking to human speed. Just gazing at my little picture, there's no wrong guess here. There's only guesses. They're all guesses are good. I won't say that's good. You ever see those people, AG on their t-shirt? All guesses are good. For that.
Can you repeat your original question?
So if we're looking at my little picture here, I've got a little drawing of this question now. My question is just eyeballing it. What percentage of the area in my little drawing under the curve have I shaded in there?
Guesses are good.
Yeah. Oh. I mean, it's way less than half, right? I mean, you can tell that. Maybe a quarter, maybe the lower half. So like half of the lower half, a quarter. That's a pretty good guess. Yeah. So something like a quarter. I might, as a nerd, I'm familiar with the curve. This little middle chunk, if my drawing is good, it's got the big chunk. And then past -1, like if I drew this down here on a perfect curve, oops. See how there's like, that's pretty big. The better you draw your bells, the better your guesses get. So I'm going to guess less than a quarter, but a quarter is a great starting guess. So let's say a quarter or a little less of the area. And then as soon as you've got your guess in mind, you just calculate it. And that like with the computer, we switch to looking to the left. So we'll see a less than symbol down here. All these numbers here, like that -1, that is on this x-axis. So like the comparison numbers go in this box here. So that's where I'll type my -1. And the moment I've typed it, I've got my buddy. The area here is about, well, to the nearest whole percentage, it rounds off to 16%. Yeah, less than a quarter. And if it's anywhere near your guess, like within 10%, really, I would say, because my drawing is not accurate, then you've got a good guess and you're starting to see these probabilities and process them a little bit in your own way. So that's how I do this. That's how I get these things going. So let me get my result up here into the notes. Let's call this one 1587, or about a 16% chance a value is, let's say, more than 1 standard deviation below the mean in a normal curve, Yeah, so what's up? Oh yeah, I'm gonna move this. Let me put this, hey friend, come over here. Like that. See that? So that's what I do. That's my dreams of calculations. Yeah. Yeah, GeoGebra, and we're at if you go to perspectives, we're at the probability calculator. You bet. Yeah, so geogebra.org/classic #probability. Oh, cool. And I missed the 15% guess in the chat. Notice that the correct value is between the two guesses. That's often the case. If you get enough people looking at something and making a numerical guess, the more people guess, the closer the average gets to the right answer. It is like a full downpour. That's wild. That's so loud and cool. Yeah.
Cut out your front, it says 6%, not 6%.
Oh, I mistyped. Thank you. I think I didn't push the button hard enough. But yeah, so watch out for typos, but a 16% chance of values more than 1 standard deviation below the mean in a normal curve. Once I've got this vibe, I try to just get these problems done, close to human speed. So for the second one, I'm just going to grab my pen again. Just going to grab draw another little drawing, a little bell. I always label it 0 for this. I label the mean, I label the standard deviation. And then sometimes I'll tick off the standard deviations. About 3 should get you out to where the bell touches the axis or so. Okay, less than 1.5. Well, there's halfway in between my two standard deviations, about 1.5. So that's my notes. I'm showing my work to myself in my notebook. And now, now my guess should be even a little better, right? Because I know the previous one was about 16%. What do you think? How much lower would this one be? Eyeballing it. There's our little guess right there. What are we doing here? What is that number area-wise? That artistically drawn little arrow, it does not look like an arrow. Wow, it's so rainy, it looks foggy. That's kind of cool. Or is it foggy and rainy?
A little bit.
I was looking
Yeah.
at the trees, the tree line, the trail thing.
This is
A little
pretty
misty,
cool.
I guess.
Sorry?
A little misty.
Yeah, it's misty plus rainy. But it got like more misty, like right when it got super rainy. Pretty cool. I mean, I'm just gonna cut it in half. We had 16% before. Would you buy 8%? Like kind of the same as I can see that it was medium big and it's gonna shrink down. It's gonna lose a good chunk of that area. And all I gotta do to make the calculation to check my 8% guess is just dump in my 1.5 right there. Oh, I overestimated a little bit. It's between 6 and 7% probability of being that far below the mean or further. So. Oh, I did finish grading like my online classes midterms this morning. So we're going to get into your midterms this week for grading for real. This is the week. But the pace of the online class is faster than the in-person class for design reasons. So they had like a couple probability questions on their midterm. Don't make the mistakes I'm making here today, or try to avoid them, like missing a number when you're typing really throws the numbers off a lot, right? Like sometimes I see people on a midterm forget that zero after the decimal, and you shift from about 7% up to like 70%. So just be careful, go slow when you're recording your results or typing them up. If you're using a computer, no shame in copying and pasting results, because then you don't have a typo and you save yourself a mistake and earn yourself one more point in your academic career. Whether you want to draw a little picture or not, would someone, just to check out who's messing with GeoGebra and how it's working, would somebody please calculate that next one for me? The chance that a value is more than 2 1/10 standard deviations above the mean in this world here. Oh, cool. We got a check already in the chat. So of course, I'm nerdily drawing a drawing while you're quickly calculating, but there's my 0. There's my 1 for standard deviation. There's a 1 and a 2 and a 3. And yeah, that area out there is going to be very small. I guess, well less than 5%. And then when I double check it, oh, I got to make sure to look off to the greater than direction. So I'm switching to the right-sided, pointing off towards the big numbers bracket. Come on, little guy. And then we switch over to correct value, 2 1/10. And looky there, 0179. Great work, Manjula. That's excellent. Sometimes people ask me about like, how should I round these numbers off? I just hold on to whatever the computer gave me, like, and then if I feel like rounding off, I'm kind of role modeling it or about, and then I round it off how I like. 2% is, I'm not worried about those 0.1% right now, but there are settings where there's small differences in likelihoods and people might be concerned about that. You pick that up in the setting when it's important for the context. Last little example here. I'm going to spare you one more little drawing, but that one, when we're between two values like that, we want to use the between two values button there, the brackets holding the values in between two numbers. And when we do that, come on, little buddy, we can go between two numbers, lower value, -1 2/10, positive value, 2 1/10. And that's a large amount of area. I probably would have eyeballed it and said 90% or something like that if I'd made that sketch myself. But we're looking at about 87% of the area under that curve right there. Pretty cool. And so as you get used to using this tool, just, if anything goes awry, like your results are coming in way off what's in the back of the textbook, for example, bring that question into class. We'll double check that the technology is working well for you. All right, cool. Yay, yay. Where can we find those brackets in GeoGebra? Oh, okay. Well, the first place you want to be is on that page right there. So you want to be at geogebra.org/classic#probability to land right here. And then right under that normal menu, you should see those 4 little options. So double check that. And if they don't show up there, check it out. Maybe I can peek at your screen during the break if there's an issue, and we can get a little individual troubleshooting on the break. All right, cool. Yay, computer. Much, much better than the olden days of looking up values in the backs of textbooks. Maybe it's the same amount of errors got made in the olden days because reading a big table of numbers, it's easy to get in the wrong row or the wrong column by accident. Though I've already role modeled that while you're using a computer to do calculations quickly and accurately, you can still type the number wrong. And whether it's typing the result wrong or typing a number wrong during the calculation, one missed key will throw off your work. So kind of like driving, just go slow enough to be safe and not make mistakes. That's the idea. All right, percentiles in this world of normal curves work like percentiles anywhere else, like in data sets. That's the percentage of observations falling below a chosen data point. Graphically, percentiles are the area to the left of, like, below the curve, to the left of the value whose percentile we're talking about. Here, that's Pam's SAT score from last class. She was red last time, so let's go Pam's percentile. Oops, let's make her red again. Well, if you were gonna just use their drawing, just estimating practice, what would you guess that percentage to be, give or take? Or based on knowledge we learned on the previous set of calculations? About how much likelihood is it to be more, sorry, from one standard deviation above the mean down? About how much likelihood should that be? Oh, someone said something in the chat and I couldn't see it. Yeah, 85% is a good visual guess. You buy it? Like, not quite 90%, but dang close. I like that guess. So if that feels good to your eyeballs, and your guessing brain, you're kind of with me and Manjula. Let's go calculate, then calculate. I'll just head over to GeoGebra. I just want to have the notes here. We need a normal distribution. The mean is 1500. The standard deviation is 300. And Pam's score, X Pam, is 1800, like that. I don't have time in my notes to draw my little bell. If I'm typing, for example, and I don't want to grab a little drawing tool, that N for normal, mean, then standard deviation is the typed shorthand for that. Back over to GeoGebra, and I can quickly double check our guess. See, remember, I don't have to do any standardized scores, anything like that. I just grab a 1500, the mean for the scholastic aptitude test, 300, the standard deviation for the scholastic aptitude test, less than for a percentile, and then Pam's score at 1800. But that GeoGebra's got a drawing just like the drawing on the slide, just different colors and slightly different shape because of the aspect of the window. But there we go, 8413. She's in the 84th percentile. Great. And for my notes, I'd write PX less than 1800 equals 8413. Kind of how I show my work for a calculation. I just make sure the output and input are clear. And then she's in the 84th percentile, rounding to the nearest value. Nice work, Pam. You fictional scholastic aptitude test taker, you. Mellow though, pretty mellow. Just once these calculations, you know what's being asked. You've got a powerful tool to do the calculations quickly and accurately, and you're in great shape. Again, the math under the hood here that finds the area under a smooth curve, that's calculus. It's specifically a process called integration. If you really love areas under smooth curves, calculus sequence, go for it. And if you don't super love them, just remember you can find them quickly and accurately for all of the statistical versions of these curves with technology. We've got normal and many other, like student, chi-squared. They're not all symmetric. F distribution's not symmetric either. We meet the other ones in those four will all meet in STATS2. That's my little ad for STATS2. There's kind of more curves to meet, more probability situations to talk about there. But don't worry about that if you're not taking STATS2. Okay, now they can flip the question around here. Finding percentiles from the standard normal curve, see what they're doing? Instead of asking us to find a area under the curve or a probability, they're giving us a percentile or a description of area and asking us for the number that gets us there. For the first one, it's not that bad. They've already drawn me a bell that's labeled nicely. I can just read what they've got here. Which z-score corresponds to the 50th percentile? So they mean that if I color in, oops, the 50th percentile is the value that's above half the area. So if I color in half that area, so artistic, look at that. I'm sort of near the lines. Let's see that. And then if I'm not confident in my drawing being good, that's 50% of that area right there. And their question is, for the percentile, well, what's the cutoff down here that gets us 50% of the area below the value? Any guesses? Z is that cutoff. What number cuts off half the area below the number?
0.
Totally, 0. It's perfectly symmetric. So half of the area is going to be below 0. And we can see that back in our calculation world of GeoGebra when we head back and reset. Oh, good mean and standard deviation are at 0. Go to less than. When you want to find a cutoff, so when you don't know this number, want to find a number on this scale here, you can enter your area, whatever your area is up here, you can enter your area right there, as long as you're looking in the left tail or the right tail. So that's relaxing. We can just double check that very well-informed guess by just typing in 50% right there in decimal form. And same drawing as my drawing, just a little less artistic and a little more accurate, showing half the area below the value 0. Now 0 is just right there. Inputs and outputs you can input either thing here, the values on the axis or the area under the curve, as long as you're looking right or left. Pretty cool. So next one, what z-score corresponds to the 20th percentile? I'm going to go all the way. I'm going to make my little drawing, but I'm going to cheat. There's a bell. I'm going to steal their bell. Come here, bell. There's 0. The 20th percentile. Well, I know 16% is below -1, so it's just going to be a little bit. I'm going to say like that. If this here, that little messy area, if that's 20%, if that's 20% of the area, I mean, my guess is going to be closer to -1 than to 0. -8/10, something like that, -7/10. You buy that? So just get in my mind, there's what I want to know. That number right there. Let's go calculate it. Relaxing, we're already looking off to the right. You just want to drop that 50% down to 20% right here. Oops. No typos. And hey, my first guess was -8/10, and this one lands. The z-score that's at the 20th percentile is -8416 after a decimal. It's kind of cool. So PX, whoops, below -8416 is 20. That's how I sort of show what I did calculations wise. And then I got 20th percentile of z-scores is about -8/10, kind of like that. Oh, interesting comment in the chat. Not getting that result. Let me just double check. There's a few ways to make, there's a few ways for this to go awry. I'll put it that way, and I've done them all. So let me just show you everything I do to make this work correctly. I've got to make sure I'm at normal with 0 and 1. So I'm talking about z-scores. Since it's a percentile, I got to make sure I'm looking off to the left, so the left facing thing. And then I put the area goes. Now this is my input, the 20% there, because that's my area here in my drawing. Does that help clear that up? It'll let me know if it helps. But yeah, it's flipping around the input and output. It's not super obvious how that works until you get practice and get a feel for how it goes.
It
But yeah, let me know when things go awry. And of course, individual support. If you're in the Zoom world, we can do that screen share on the break so I can look at your screen. Relaxing. What z-score has 70% of the area to the right of it? To the right just means I've got to turn my thing around in GeoGebra. So let me get my little notes here. P, Z greater than what number is going to be 70, well, the 70% of the area. Let's go see. I'm already in this world. I just gotta flip around to the right-sided deal. Instead of the 80% it's sitting on because it just stayed where it was as far as the z-score. Switch that 80% to 70%. And looky there. That z-score, it's slightly less than -1/2. So is the, let's just say z equals -5244 is the z-score. 70% of the area under the curve. It's right. Cutoff scores. They're kind of abstract here. A few more examples where they're less abstract and a little slightly more interesting than just standard deviations from the mean. But these are good, just practice for getting our facility with the computer stuff. All right, cool. What is the next slide here? Is it a good one or a boring one? Oh, it's pretty good. It's about ketchup, and people love ketchup. Although ketchup makes people hungry. So let's take a quick break, and I'll go eat a snack, and then we'll come back and talk ketchup. Yeah, sound red and sugary? Great. Okay, let's get back here at 3 minutes past the hour. Or as close as we can to that time. See you soon. Damn, back at 12:03. I ate the whole cinnamon roll and everything. That was awesome. All right, welcome back, welcome back. Let's look at some more normal distribution stuff. Quality control. At a ketchup factory, the amounts of delicious sugary goo, which go into bottles of tomatoey ketchup, are supposed to be normally distributed with a mean of 36 ounces and a standard deviation of 11/100ths of an ounce. Whenever I see that little phrase, normally distributed with mean and standard deviation, the first thing I do is I grab the nearest pen that matches the color of the context. This is the world of ketchup. And I draw a little bell somewhere nearby. I grabbed a thick pen this time. That's okay. Maybe I'll switch back to a regular pen. Center here. 36 ounces, mean, and 11/100ths of an ounce standard deviation. So my notes, even before they ask me anything, I've already kind of put myself at human speed into the world of varying amounts of ketchup poured into ketchup bottles at this factory. Okay, if the amount of ketchup in the bottle is below 35 8/10ths of an ounce, the bottle fails the quality control, fails quality control inspection. That's not quite 2 standard deviations below the mean. So if I go out here, say that's 3, 2, 1, I don't know, something like this. I don't know. That's my guess right there. That little area. Let's call this 35.8. My handwriting is bad, but my drawing, it's the best I can do. But see how my little notes, as I read the problem, I'm just making a picture of what they're asking me. And then I've already got a sense, this is unlikely. It's going to be down there in the 5% range-ish, something like that would be the probability a randomly selected bottle fails quality control for being too light. In their notes, they've got it in the world of symbols. Their capital X amount of ketchup in the bottle, that's my curve, that's my drawing. They just write down the mean and standard deviation, and in their notes, they've got the symbols that we're going to see over there in GeoGebra. So it's good either way. If you're taking notes without drawing a picture, just make sure somewhere nearby you've got the mean, the standard deviation, and what your goal is, with some sense of if you're looking down at the lower values, less than, or up at the bigger values, or if there's some kind of other way to look at the numbers. But once we're here, cool. We can just go immediately over to GeoGebra. We've got a drawing that has all my notes in it. Okay, I just got to reset my mean to 36 ounces of delightfully sugary tomatoey ketchup. Reset my standard deviation to 11/100ths of an ounce of unhealthy yet delicious goopy gooey ketchup. Go back to less than, because we're thinking about bottles that have too little ketchup in them. That's obviously a crisis, because if you're expecting like one more hot dog's worth of ketchup in a ketchup bottle and it's not there, I mean, that's terrible. That would be horrific. It probably means the ketchup machine needs adjusting for pouring at the factory. And then it's less than, there's my range. I just dump in my 35 8/10ths. That is the bar for being, it's acceptable to be that light, but no lighter. And looky there, I've got, I don't know, an 0.345 probability of that going that way. So in my notes, probability X less than 35.8 is 0.345, or about a 3.5% chance that one random ketchup bottle is a little too light for quality control. Oh, didn't use my red pen, but I've got a computer, so I got my red pen for my notes there. As they're ketchup notes, like they got to be red. It wouldn't make any sense to use any other pens. In fact, I would get a little sad if I'd used like a blue pen, for example, about ketchup. Just in a world with red pens, you want to use them when they're nice, ketchupy, rather than when they're mean, like judging. All right. Now let's compare our result to how the book writes this up, and there will be a little hiccup here. Remember, I mentioned that some aging statisticians still like the oldie-fashioned switch to the standardized score, the Z-score, and then go look up the number in a table in the back of a book. So oftentimes when we do our calculation and we compare our results to the book, it'll look a little different. And let me show you how that looks. Their drawing's the same, but they won't show you this drawing in the results in the back of the textbook when you're checking your homework. They're just reminding us how it should look, that the area should make sense graphically. Pardon me. But look in their work, their first step. Huh? Z, what? Negative 1.82, huh? Like if you looked up your result in the back of the book and that's the first line, you've just calculated your 3.5% or so. Just remember that Z-score is the old-fashioned way to do this problem. It's just going to be in the book for almost every normal distribution problem because whoever the editor was old enough to think it's still important at this point in the history of Earth for people to know how people did stats back in the 60s. In any case, their next step might look a little weird too. Oh, wait, they didn't even write it down, but their PZ less than negative 1.82. That's, you always rounded off Z-scores to the hundreds because that's how they look in the tables in the backs of stats books in olden times. And so they're always going to have results rounded off to like 3 or 4 decimal places, but sometimes they'll round off a little differently. Like if I rounded our result, it'd be 3.5%. Theirs rounds off to 3 4/10%. You'll often see results in pretty much the next few sections of our textbook where we're dealing with probability distributions. You know, wherever you're rounding it off, it might be off by 1 at that point because of just using different kinds of technology. You've got modern technology. Sadly, our textbook, like the majority of modern stats textbooks, still uses old-time technology. But in any case, shouldn't be too far off. And if there's ever any confusion with that stuff, just ask me and I'll remind you of how to avoid that confusion and double check your results are good. And you should just cruise along. Once you've got this lovely tool working for you, you can do any normal probability question quickly and accurately, as long as you've got the correct mean and correct standard deviation. You're good to go. Good old ketchup. Is this the quiz? Did I just grab this practice problem for the quiz? Let's go see. Let's just go find out. I might have gone because I like ketchup a lot. Do I like ketchup? I don't like it as much as my little kid, but I like it a lot. I liked it a lot when I was a little kid. So I think I like it. Normal distribution quiz. It's sugary. Details boring. Start quiz. Oh, no. It's about a different question. Let's wait. We'll wait. We'll hold off. Body temperatures, we'll get there soon. Let's just wait. It's about the highest 10% of human body temperatures. We'll get there. How about this question though? Just to double check our skills. If the amount of ketchup in a bottle is below 35.8%. So that's the likelihood we found before, about 3.5% of a chance, or above 36.2 ounces. Then the bottle fails quality control. Same mean, same standard deviation here. What percent of bottles pass quality control? That's not bad. I can draw the picture right here. They want 35.8 at the lower edge there, 35.8. Brilliant mouse writing. Up to 36.2 up here. Whew. Okay, the mouse writing went down 2 levels at that attempt there. 30. 6.2. Still centered at 36. Same standard deviation. And the area that I want is that central, the folks, the ketchup bottles that are in that good weight range for this factory of delightful ketchup makers. Okay, just making the drawing, I can already see options A, B, and C are completely wrong. They're not even close to tons of area under the curve. It's either D or E. Without even thinking about it, I can just go quickly check in GeoGebra. So that's what I'm gonna do. Or I could think about it based on my previous result if I was a little, that type. But it's between two values in my drawing. So I go to the interval setting, the two brackets holding the values in between them. 35.8 is the lower boundary. 36.2 is the upper boundary. There's their drawing. Result 93 plus percent, 93 and 1/10% of the bottles would flunk. So I've got probability is 93 and 1/10%. Sorry, of bottles pass, right? Passed QC, short for quality control. Okay, just double check my result with the slide. Probably would like to be able to read it. Okay. But there you go again. See, look, they've got their Z-score for the lower value, Z-score for the upper value. They're symmetric because they're both basically 2/10 of an ounce below and above the standard, the mean, sorry. Then they're back here in the world of Z-scores. So, but they come up with, see that? They've just got a little bit 9312. They're like 2/10,000ths different than our value because GeoGebra does show 4 decimal places. So in any case, it's close enough, right? We just ignore that last decimal place and that looks good. 93 and 1/10 with a little extra because of the difference in methods. No problem. Cool. Yay. Good job. Ketchup good. Yeah, yummy ketchup. Oh, clear out all my messes. Oh, this is like the preview. This is the preview of our quiz. Let's go to the world of body temperatures for healthy people. This is a world I visited in great detail the week of Valentine's Day, when first my kid got a really bad fever, then I got a really bad fever. Then my co-parent, well, along with some even worse symptoms, also dealt with a fever. Phew, I thought about this slide when I was sick. The normal distribution, so normally distributed, temperatures of human beings are centered at, what if I make it easier to read? I'll make my drawing. They are centered at 98.2. And standard deviation, the variation there is 73 hundredths of a degree Fahrenheit. So, okay, what is the cutoff for the lowest 3% of human body temperatures? So in my little notes, I'm just going to draw in, I'll color in, I'm eyeballing it, 3%. There's my 3% area right there. I'll label that 03. And then the question is, what is that cutoff score right there? See that? That's my little notes. Whenever I've got a percentage given to me, I just eyeball it. It looks like it's going to be, I don't know, a little bit less than 97 degrees, something like that, based on the drawing. 96, 97 degrees, something like that. But that's all there is to it. I just got to go figure this out using the tool at my disposal, my little buddy GeoGebra. Cool, I got my drawing with my mean, 98.2. That's my mu. I was just remembering my Mew from Pokemon. Their name was just Mew because I traded for Mew to trade somebody. So cute. I loved that little character. 73 hundredths of a degree for standard deviation. Okay, cool. Centered at 98.2. Great. And then I'm going to look at that lower tail. And remember, when you want to find an area, so if you want to find an area like this, if that's your 3%, you put that in the area side down here. So I'll put the area there. 3%, those are the lowest body temperatures. And the cutoff score is A. Did I say like 97, between 96 and 97? Just from my little human speed drawing. Makes me feel good about my bell art, but also we've got a good result there. So probability X less than 96.827 is 3%. That says about 96.8 degrees Fahrenheit. Oops, degrees Fahrenheit is the third percentile for a human temps, right? Body temperatures for short. Pretty relaxing. Like once this technology starts to work for you, it's not bad at all. You just use it again and again to get the correct result by just being careful to not make a mistake in the path. Reminders, the mistakes that are easiest to make are not remembering to adjust the mean and standard deviation before you do a problem, not setting up the thing to look in the correct direction, and then, well, making sure you're getting your probability or your number on the scale put in the right place down there for calculations. And of course, avoiding typos along the way. They're an easy way to make a mistake anytime we use a computer, whether it's for math or statistics or just writing a note to someone we care about. Or filling out a form for something boring we have to fill out a form for. Right? Oh, let's go back and check our result. Oh, same drawing. They made one with a computer, but again, I'd say the more times you draw a little bell, the better this concept will sink into your, hand, eyes, and therefore your brain and your heart, like your whole body will get a better sense of how this works if you make those little bells yourself. There's the Z-score. I'm just going to say, I don't really care that third percentile is 1 in 8,800 standard deviations below the mean. Not a big deal. I mean, it's interesting for what it is, but it doesn't tell me what I want to know, which is their result, rounded off to the nearest 10th of a degree, just like ours. So we're in great shape. But I wouldn't have been surprised if it was 96.9 or 96.7. That wouldn't have shocked me at all because of the difference in methods. So good stuff. And you'll notice in their calculation, there is a bunch of, see this stuff? There's a little funky little math to do if you're going from percentiles back to values to undo the Z-score calculation. We didn't have to worry about that. So that little piece, that's another little old-timey, I'm not worried about that. I'm just worried about the value and getting it right using my buddy technology. Cool. Now, are you ready? This is the quiz question. Here you go. Can you GeoGebra this for us? It's on the quizzes, written exactly the same as on the slide. Body temperatures of healthy people are distributed nearly normally with a mean of 98 2/10 degrees Fahrenheit. Standard deviation, 73 hundredths of a degree Fahrenheit. What is the cutoff for the highest 10% of human body temperatures? These are people who run warm. So these are the folks who you see wear sandals and shorts this month. Because their bodies are already all warm. They don't need long pants or socks. They're warm. And they hate summer. Oh, wait, am I wrong? Are they extra cold because they're hot? Maybe I'm wrong. Maybe they need 2 pairs of pants, double socks. See how it works? Yeah, little pick. Gets me in the world of this. That number calculator right there, that history number. If you're out in the world of the Zooms, you can share it in the chat and we can double check you in the room. If you're in the room, you can just say your result aloud when you've got it. Or you can wait till someone else says theirs and then say, hey, I'm the double checker. I got that too. And we're in great shape. We can already see which answer is obviously wrong. I'll get rid of it. Can't be 97 and something degrees. That's below half. And we're definitely above the halfway point here. We're above 98.2 degrees. But I wouldn't be able to guess which of those 99 and something tenths is correct with my eyeballs. I would just be like, huh, interesting. One eye. What's that?
Are you asking us a question?
Yeah, this question.
Oh.
Oh yeah, what'd you get? And 1/10, the first option is not bad. Agreement? Anybody else back that up? Back up Chanel's result? Yeah, couple nods. All right, cool. I'll just triple check it and give it for the world outside the room. Back to probability, GeoGebra. I'm still in the world of 98 and 2/10 mean and 7,300 standard deviation. Just double check I've got those right. We're looking for the upper tail. So I shift around to the right-sided bracket pointing toward the big numbers. I don't want 97% off in that direction. Just 10%. I think I heard the sound of someone cute at somebody's house. I love that. Or is that outside here? Is that there? Right there. There's really cute people right outside our classroom, of course, at the daycare. Yeah, 99 and 1/10 degree. Perfect. Great work. So grab that 99 and 1/10 option. Oh, wait, where's our quiz? There it is. Give me my pointer. That one, second option is perfectly good. Check that box. Submit your quiz, get your point, and be a relaxed, happy, normal distribution liker. Yeah, great. Clickety clack. Great, 90th percentile. Now wait, let's think again. Hold on. If those are people who run hot, when it's cold outside, they should feel relatively more cold, right? Because if you normally run hotter than everybody around you, when we all feel cold, your normal body temperature is further from the coldness that we feel. So you might feel a little more cold, or it might run you into, or it might make you feel hot inside, so you want to wear shorts. I don't know. I need to do more research. I got to ask Lindsay, my friend who wears shorts and slip and sandals all through the winter, what her body temperature is. That's just anecdotal, though. I got to ask her in all of her shorts and sandals wearing friends. Again, look, they've got the little Z-score. They've got the funky little bonus calculation you don't need to worry about. But using our buddy technology, we quickly and accurately got that same value. Again, if it was off by 1/10 in either direction, that should not shock. But sometimes if it's ever confusing, the Z and these bonus little calculations, as I know that if someone walks away from this discussion today and picks up their book, in 3 days to start their homework or something, these little details I'm talking about might not be in the front of your mind. If there's any confusion during this homework, be sure to ask the question. That way I can double check if it's how it's getting set up and solved, which would be an issue, or if it's just these little confusions with different methods. That's, well, a different kind of issue, but not an important one. And once we understand it, we're all pretty much good to go. This is a fun little slide that if we understood this stuff better and had like an hour to like sit and talk and chat and draw drawings, would be a cool activity, but we don't have that time. And since this is new ideas, let's just kind of walk through these together as a team. They're just all little true and false statements. They care which ones are false, but really just think of it as true or false for all four. Let's just take them one at a time. And let me help out with some visual help to add to the questions. First one says the majority of Z-scores in a right-skewed distribution are negative. Is that even possible to think about without looking at a picture of a right-skewed distribution? To me, I cannot imagine what the result would be without going and checking how it looks. So I'm just gonna make a fake one up on the slide here. Let's pretend there's a different ketchup factory where instead of the ketchups being equally likely to be light or heavy, they basically never go down below a certain amount of ketchup. Oops, that's not a curvy line. They never go down a certain level of ketchup weight. And then there's the most common weight. And then when they start to fall down, they actually do have kind of a issue with bonus drips, little extra drips getting into those ketchups. And we've got a very skewed to the right, a lot of stuff taking us away from symmetry toward the larger values. Okay. Now let's think here. The Z-scores tell us how many standard deviations values are from their mean. Okay. Now, the mean value in a skewed distribution, well, there's no center like there is with a symmetric distribution visually. We have to think of it as being at the balance point. Think of the graphical balance point for the distribution. Let me just sketch one in here. Way back in chapter 2, I sure liked to draw small orange triangles to balance out things at their mean. Oops, hey buddy, just come with me. Just let's go. Buy it. The peak is going to be a little bit below the mean because that's where the heaviness is, but the tail will pull it above the peak because, well, you just got to get out there and balance out all that weight in that tail. Heck, I might even need to go more near the tail. I can't tell, but see what I mean? Okay, now, also back in like chapter 2, I think the first section, we learned that if we grab the median value for a skewed data set, and oops, we tended to draw those. I like a green line to tear things vertically. This should cut the area in half. So half the area on one side, half on the other, like that. Again, I'm just eyeballing this as quickly as I can. I don't think they're perfect. But the median, well, once we get just a little bit past that peak, the other side, the tails, I'm imagining it's just the tail there looks like it has about as much area above that green line as there is back near the peak to my eyeballs. By that, so median gives us half the values below and half the values above. Median's the balance point. Skewed right distribution, because the balance gets pulled out toward the big values. The mean is greater than the median, right? Heck, and that was an important thing they said back in the slides way back when. Skewed right distribution, usually, especially if they're unimodal, you're going to see the mean to the right greater than the median. Okay, now can you tell me if number 1 is true or false? That's the picture. That's the relationship. The median's the green line. So half the values are below the green line. Half the values are above the green line. Are the majority of the z-scores are a negative z-score? Remember, that's just a value below the mean. So is the majority of area there below that balance point now? Majority of the area. See why these are hard? Oh, wait, let me just draw, let me label it even more clearly here. Area-wise is green. Below that green line, there's half the area. And above the green line, above there, there's the other half the area. See that? Half the area below that green line, half the area above that little green line. Come on, buddy. But see where the mean is? Are there more than half the values below the mean or more than half the values above them? It's not right there at the half line. It's off. Below. Yeah, because we're talking about getting all the way. We're getting, give me orange shading. We're getting these half of the values down here. That's half. And a little more from the skewness. So maybe it's going to be, I don't know, 60% or something like that in my bad drawing, or 55%, but it's the majority. So that one is true because negative is just below the mean for z-scores. So this one's true. Or truer, as I spell it. Twice. And one bonus time, I did it one bonus time. True. Okay. In skewed distributions, the z-score of the mean might be different than 0. Remember, z-scores above the mean are positive. Z-scores below the mean are negative. So the z-score at the mean has to be 0 every single time. It's just how the calculation works out. That's definitely false. That you're never gonna find a mean that's different than 0. So that's false. Or say, as I spell it. For a normal distribution, look at this one. The interquartile range, the distance in the middle that captures half the data is less than twice a standard deviation. Is it even? I don't think it's clear what they mean. Let me draw the picture. Let me draw the picture for you. Now they're talking about a normal distribution, not a skewed one. So here's a little bell curve down here for part 3. Okay, now remember the mean's in the middle because it's symmetric. The standard deviation takes us that far out to capture, remember the rule, 68% of the area is within one standard deviation of the mean. And if I do this, draw one little measurement there, that little measurement, that's 2 standard deviations. So that's 2 times the standard deviation. Oof. So 2, oops, give me blue now for that drawing. 2 times the standard deviation catches the center, or sorry, 68% of the area about the mean. Interquartile range captures how much of the area? Do you remember? How many of the values back there in the data world? Do you remember? Well, it's like from the first quartile to the third quartile. Yeah, so there's 2 quarters in between, or 50%. So we'd say down here, IQR only catches the middle 50%. So that's different. It should be a little tighter. Interquartile range shouldn't take you out quite that far. So interquartile range is less than 2 times standard deviation. I agree. 50% is less than 68%. So the interquartile range should be less than 2 standard deviations. Whew. So that one's true. Green pen for that one? Sure. Okay, last one. Z-scores are helpful for determining how unusual a data point is compared to the rest of the data in the distribution. Remember, all they tell us is how many standard deviations from the mean a value is. So if I tell you there's a distribution and a number has a z-score of 20, does that sound like a rare value compared to one whose z-score is 1/2? Or are they still just too new to have any meaning? Because if they're too new, then the question's just useless. But remember, a z-score, just in the picture at the bottom, think of the tick marks, like z-score -1 is right there, -1, -2, -3. So like z-score -3, we're getting out there into the realm of very rare. -4, I almost never even draw a graph that goes out that far to -5, -6, etc. Same thing's true in the other direction. You go up 1, 2, and 3, and you're almost at the edge of the picture. You go 4, 5, 6, 7. If you get a z-score that's like above 3 or 4, it is telling you that's a dang unusual data point. Big z-scores in magnitude, whether they're positive numbers that are big or negative numbers that are further and further below 0, they do compare in a nice way in a unimodal symmetric zone. They do that. That's their job. So that's true. All right. Oof. Those aren't just straightforward, read the four options and say, two's false. They're like, let's talk about a bunch of subtle ideas from the entire discussion from today. Not really, I don't know. Kind of a weird slide, I think. But in any case, let's check our result. We only got two as false. They agree. I think we're in good shape there. Yeah, I think there's one more slide. Yeah, but this one, it's talking about this thing called the normal probability plot. This is going to be easier to talk about when you can mess with it a little bit and see it in a context that makes a little more sense to us. I'll have us make one in the lab. We'll use the counted data set to look at the ages with one of these. And when we have it to look at in context, I'll explain it better. I just think it's easier to explain when you've got a little more to talk about than just heights of basketball players. All right, so but we'll have these bonus examples of heights of basketball players and just heights of random dudes. Bonus examples if we want to look at them later. Okay? But so we'll talk about that later. And now it's like quarter till. Perfect time for a break because we just wrapped up the slides, got the quiz done. And it'll give us like a nice solid hour-ish to work on the lab, which is about the right amount of time. So we're gonna push the other topic into next class, but we're gonna get the lab done today. So the big goal is the lab success. Take a break, come back here at 6 minutes or 56 minutes after the hour, 12:56. And we'll work on the lab and we'll have a good session. It's a shorter one than the last couple, so it's a little bit less of a mental and physical experience, but it'll give you some experience messing with GeoGebra's normal distribution and learn a little more about how it feels to use a model rather than looking straight at the data. And when that makes sense, hopefully. All right, see you soon.
Yeah, I'm going back.
Thank you.
Whatever part of me is Austrian and German is so disappointed in myself whenever I'm late. All right, team. Let's go. Let's go work on this lab. It's a good one. It's not a long one, but I think there's some interesting stuff here. We're gonna work just where we are. And because we have a lot of folks in the Zoom and the room, it's about equal sized groups. Think of us as all one group. We're all one group. I'm on everybody's team. Every question is good. Most questions that you have, probably at least half your classmates will have. So we'll kind of try to work as questions arise. I'll mostly discuss them up here. That'll help out everybody, I think. So I'm heading into content lab. It's part 5, normal distribution. It's the shortest one, which is good because we've got about an hour to work. First thing, as usual, I'm always going to make, I'm not in my PCC account, so I got to sign into the correct email account here to get my own copy saved in the right spot on planet Earth. So getting into my PCC account. Publam, yeah, that's me. Zip, zap, zib, yep, it's totally me. I'll verify it as many times as you like. Cool, now when I open up this piece of this lab, normal distribution, the counted, part 5. There's me and the late great Rojo the llama. And now I can make my own copy and it'll save to my Google Drive where I need it to be. So that's always my first stop. File, make a copy. I stick with the Google Doc. Of course, you can download this if you like. And my style is just name of the quarter in terms of season and year. Winter 2025. Cool. All right, great. Now let me get you all familiar with some of your goals and settled into the technology once more, because we've stepped away from spreadsheets and data analysis in GeoGebra for a while. So I'll just give you a couple of reminders to get you into the work, but also just our big goals. Well, we're gonna, again, we're gonna use the ages among the counted from 2016, and we'll just still practicing getting our data from a spreadsheet over to GeoGebra to get a graph and get the summary statistics calculated quickly and accurately. We're just gonna look at the entire group. We're not gonna do any disaggregated stuff like we did on the previous numerical data lab. So it's gonna be a little less complicated, and that's cool. The third bullet, the last bullet, is the important one. We're gonna consider how well the normal distribution models a data set, and we're gonna do that like kind of 3 different ways as we work through this. 1, just with our eyeballs. 2, analytically thinking about likelihoods and how they should look if things are normal or not. And last, we'll look at that normal quantile plot, that topic right at the end of the slideshow from before the break that I said we'd talk about in the context of the lab today. That's actually the very last question on there. So that'll be our wrap-up discussion at the end of our work time. Let me just settle you in to just the technology again. We're going to work with the 2016 data spreadsheet for the counted. I've got a copy, so I'm going to open up my personal copy. But you can just use that link. You just have to copy out the ages. Right. Yeah, the age randomized variable on the second sheet, that's our goal. You can just open up any copy you want. This link will take you to the shared copy. Should work just for copying and pasting. I always grab my personal copy just because I'm a nerd. So if I go to winter 2025, how does the computer know? Just because I'm talking about it? Is the computer just listening to me? Winter 2025, the counted 2016. That's what I want to look at, my copy of these data. Does it know because it's Monday at 1 o'clock when I normally open this exact spreadsheet? But the idea here is if you're in your own copy, you should be able to find the age randomized, that little bonus page I made on the original sheet. It's 350 rows that contain 349 randomly selected, counted cases, ages in that first column, along with their racial and ethnic data in the second column. We just need their ages. So I'm gonna copy those. Click. And then the goal there is copy those age randomized variable in the second sheet into GeoGebra Classics spreadsheet, and then double check we've got all 350 rows. Let me give you the reminder for pasting into GeoGebra spreadsheet. There is a couple of annoying things that can happen. Sorry, there are a couple of annoying ways it can go if things go badly. First, landing at GeoGebra, .org/classic #spreadsheet will put you at the place to be. So spreadsheet link. There's your GeoGebra spreadsheet link in the chat for the Zoom folks. When you're pasting in here, there's 3 ways that you could intuitively want to do it. The first one is, since I selected column A to copy it, I might select column A right here to paste them. That won't work because if I look down at the bottom, that only goes 100 rows deep. And for some reason, when it's all selected like that, it'll cut them off at 100. So don't do that. Doesn't work, even though it's intuitive. The next one that's intuitive is just tap on that first cell, A1. That totally works. If I just tap on that cell, it's got a blue frame. There is no blinking cursor in it. I can paste in my values, and they're going to fill up when I allow GeoGebra to read my, hey. No, they're not. I copied something else before I made a mistake. You got to copy the thing you're going to actually paste. So this whole thing of data, copy, now, spreadsheet, paste, and no problem. Double checking that I've got 350 data rows. I'm in good shape. It's a good copy and paste. There is a third way it can go wrong, though, that you should see. Remember, one little cell, blue frame is the good way. A whole column is bad because it will not have enough space for all the values. Likewise, if you even just accidentally double click and you can see that cursor blinking in a cell, it'll dump all the values into one cell. That mistake is so obvious that people immediately correct it, so it's not as big of a deal as the other one. Remember, one cell, blue frame, you're in perfect shape to copy and paste. Once you've got that done, you're in really good shape to go do the first few things, making a histogram and a box plot. Those are familiar data analysis goals that you worked on in previous lab work and on your midterm. So if you have any questions as you're working, just ask me, and I'll give you a walkthrough in the room or via Zoom. Second question, once you've got the graphs, to gaze upon them and answer the second question. Third question is getting summary statistics calculated. Just a little note to remember that we're going to use sample standard deviation S when we use standard deviation here in this work. Otherwise, everything should be familiar all the way through task 5.1. So go for it. I'm going to kind of work through it up here quietly until people start to ask me questions, and then I'll, of course, help you all out. Sound good? All right, cool. Let me know as technology questions arise, and I will help you out. Oh, great question, direct messenger. We will talk. The short answer is yes. That is exactly the answer I was looking for. And we'll talk about it in more detail when more folks are on that particular problem. Someone asked a question that is a really good one because number 4 here. Number 4 is not the best written of the questions, and I've never better written. So, and it's tricky for a couple of reasons. First, let me just reminders on 1, 2, and 3, you're focused in on the data set. You're making graphs of the data set. You're talking about what you see when you look at it. I didn't do that in my notes, but you can do that when you're there on number 2. And on number 3, we're calculating and recording statistics from these data. First thing about number 4 that's weird is it says in a standard normal distribution. That's the bell curve that we've been looking at all today with mean 0 and standard deviation 1. So we're leaving the data set behind for a few minutes to think about some other questions. So it resets where we are mentally. That's the first reason it's not an easy question to make sense of. I've just noticed that over the years, its placement here is odd. And then this question, what values would you expect? No need for calculations here for the following. What's the probability that a z-score would end up further from below the mean, or sorry, further just below the first quartile of all the z-scores? Does that make sense? What's the probability one z-score would end up below the first quartile of all the z-scores? Probability that one z-score would end up below the median of all the z-scores, and the probability that one z-score, z, would end up below Q3, the third quartile of all the z-scores. Tried to read that out with more detail, and then there's a great question in the chat to follow up my description. Would part A, what's the probability that one z-score would be lower than the first quartile of all the z-scores? Our direct messenger says, should that be 25%? I mean, if you're at the first quartile in a data set, what percent of the data are below the first quartile? 25%, right? So if you're at the first quartile of a probability distribution, like the normal curve, the chance of being below that value has got to be, just like our direct messenger said, it's got to be 25%. But see how this question's just the way that it's written and that it's kind of coming at this in an odd direction makes it harder to make sense of than would be my desire. But then as a class, what about 4B? What's the probability you end up below the median in a probability distribution? Yeah, 0.5 or 0.50 if you like 50%. Any of those results are good. So 5/10 or 50/100 if you think in terms of percentages, like old Ralphie. And then what's the probability that you'd end up below that third quartile in a probability distribution? Yeah, 7/500, 75%. 3/4. Yeah, exactly. So the question is weird because it's a little tricky to get at what I'm asking, but once we're there, those are the expectations you'd have. If you're in a probability distribution, you're at the first quartile, the median, and the third quartile, you should be at the 25th percentile, the 50th percentile, or the 75th percentile, respectively. Now, what you're going to do on number 6 is you're going to use the normal distribution. When you get past number 5, you'll put it together. You'll set the mean to be the mean of the ages that we just calculated back in number 3. You'll set the standard deviation to be the standard deviation of the ages that we calculated from these data. Then you'll plug in the data's first quartile, median, and third quartile. The closer those 3 probabilities get to 25, 50, and 75/100 respectively, the better a normal model would be for these data. The further off they get, the worse the normal model looks for these data. That's the analytical way of considering, is a normal model good here? And that's what we talk about in number 7. So wander through there. Of course, any support you need with any of the technical stuff, whether it's in numbers 1, 2, and 3, or any of the stuff here in 4, 5, 6, 7, let me know. And then once a couple of people get curious about question 8, about normal quantile plots, when a couple of people are there, we'll take a minute to talk about how those work, how they look, and how that gives us one more way to consider if data sets look normal. We'll peek at one more. All right, great questions. Wait, yeah. Come in your instant. good people. Someone asked, there's a couple of good questions that have been asked. One is definitely full, everyone in our group, all of us discussion question. We talked about 4 to get us through the complicated language and sort of badly asked, not too complicated question. Good work. Okay, when you get to 5, it's not that bad to just go, okay, use the mean and standard deviation from problem 3, plug them into the normal distribution. Let me do that first. So if I just go back to good old GeoGebra, I've got my statistics here, all these graphs of the data set. I can, in the view world, I can also turn on my probability calculator. If I do a little thoughtful screen sizing, I can see everything on one screen. Get the data's mean, 37 and a little more than 2/10. Did I type that right? Yeah. And the standard deviation. Be careful here. Remember, we've got a sample of these ages. So we're going to take the number S out of the statistics here, even though we're plugging it in for sigma. Sigma is the model's standard deviation. Different sigmas is what I'm trying to say. 0.5853 standard deviation. Got that typed correctly. And right there, there's the graph that right here it says sketch or make a picture using GeoGebra of this normal distribution. That's done. The second I enter the mean and standard deviation into GeoGebra, I've got a great sketch. Nobody asked a question about this part. I'm just doing it to be a good role model. It's part B that's confusing, but let me just get my little sketch here. Shift, window, S. Thanks again, Elizabeth, for the training on grabbing pictures like this one out of the internet. I'll grab that much of it. Okay. There's my sketch. And then here's the thing. The next part, write a caption identifying ages that are 1, 2, and 3 standard deviations above and below the mean. The idea there is, let's take a peek back at the slideshow from the text for a second, just to remember how statisticians like to label their normal curve graphs. It doesn't matter. Most of the ones in here that I look at that have good labels, let's get back like the standard deviations here. Notice that they're always labeling carefully the mean in the center, and they're always making tick marks that are 1, 2, and 3 standard deviations above the mean, and 1, 2, and 3 standard deviations below the mean. I just want what those labels would be if we were going to label this just like a statistician. So it's just a matter of doing some straightforward calculations with addition and subtraction. Like, we're going to have, oh, what happened there? Why did that happen? Don't do that to me. What are you doing? Yeah. So we're going to have, I'm going to do them in order of numbers, like 3 standard deviations below. Right? And then I'm going to do, 2 standard deviations below, 1 standard deviation below. And all these calculations are going to look just like, I'll take the mean value. There I'll subtract 3 times the standard deviation. Those are of the ages. So that'll look like 37 and 2/10 if I round it off. If I want to round it off, I'm going to round it off just to save typing time. But then the standard deviation is 13 and 6/10 if I round it off to that same accuracy. So -3 times 13 and 6/10. Then I've got a little number. That's -3 and 6/10. So that's like 3 standard deviations below the mean, takes us just down below 0 years old. Not surprisingly, there's 0 cases down there, more than 3 standard deviations below the mean, -3.6. And then this same calculation I did here Copy it for 2 standard deviations below. I just changed the 3 to a 2, right? Got a different number. For 1 standard deviation below the mean, I just don't have to do any multiplication of the standard deviation. I'll get a different number. See what I'm doing? Just kind of it's just pushing some numbers around to put us in the world of the tick marks that statisticians like, standard deviations below and above the mean. That's what that's asking. So a few more. And I'll just complete the whole mess. That would be my little arithmetic task for the day. Yeah, great question. Okay, 1:30. One person so far has asked me directly about double checking they're making the graph correctly for number 8, the normal quantile plot. And 0 people, oh, that same person asked me, okay, and what do we say about this question here? So when I've heard that second question from like one more person, we'll pause and like talk about number 8 as well, so everybody's got some sense of how that works. No pressure on you to be anywhere in this work so far, but I do want to make sure we get all these great questions answered at least once, especially for the folks in the Zoom world, along with, I know at least one person who's going to be watching this later on the old YouTube. Oh, cool. We have a direct messenger ready for number 8 as well. Let's just give it like 2 minutes. I'll walk around the room one more time to double check for any questions in here with anything else, and then we'll come back and talk about that all together. So quantile plots after my next tour of the room. We've got Nolan, then
It's, very. Oh, wait, no, yeah.
yeah, it's 6.5.
Yeah, no, it's, but other than that, the reason we'll just guess. What it correlates to things, right?
All right, people who have arrived at number 8, great work. About a crew of us are there. So if you're anywhere before number 8 and you want to get a preview of how it works and what it's about, just join us in this discussion. But of course, we can talk about it again anytime later in class when anyone else asks. Okay, construct a normal quantile plot of the age variable, paste it into your project. Does this graph support your conclusion from problem 7? Why or why not? Let's take that a step at a time. Making the graph is not difficult. Once we've gotten used to making graphs in GeoGebra, the data set's already there, and we've already made a couple of graphs. Those of us who've got some, the graph menu is right there at the top, and the normal quantile plot's just the last option among the graphs. So building the graph is relaxing. When you've got the graph, it's gonna have, if you have a square aspect like me, the line in your graph will be fairly like close to a 45-degree angle, and you'll see some dots. Each dot represents one of the 347 cases among the counted from our data set. And I'll explain how their relationship to that graph works in just a minute here. First, let me just grab my graph and dump it into my work. I'm going to go old-fashioned screenshot. I wonder if I'm going to remember this whole shift window key S thing next quarter, like after a whole week off. It's going to be a real test of my learning. We're going to find out next quarter. This goes in my work right here. Doesn't have to be all that big. Okay. Does the graph support your conclusion from problem 7? Well, I didn't make one, but we'll look back at problem 7. And why or why not? Well, there's going to be stuff to learn about what the normal quantile plot tells us and how it does that. So you want to start with what the normal quantile plot means and then peek back up at my conclusion after I've got that. We'll stick here with this graph. Okay. Let me go back to GeoGebra to look at this in more detail. The way that I like to get at my explanation for the normal quantile plot is like this. I'm going to make down below it a histogram. And there's a setting in histograms that we've never used, but it's helpful for this discussion in particular. There's this normalized button in here. Click. And then once I've done that, oh, come here. Come, off. Wait, where's my little buddy? Where's my little friend? Are you here?
Where was the normalized button? I just missed that.
Oh, let me show you. It's in the options. So under the gear is the options. Got this normalized button under frequency type.
Thanks.
Oh, I remember. And then under show, if you go down to show below that, hey, buddy, where is it? Did it change? Has GeoGebra changed and not told me? Hey, there used to be an option there for show normal curve. And what it would do is it would draw us a lovely little picture. There it is. Now it's there. I think I just had to refresh it. Okay. See that normal curve option? I'm going to turn that on too. That's what I want. Okay, now let me make a few more bins so it looks a little more detailed than it started with. Something like that. Okay. Now you don't have to make this complicated graph with the normal curve on it for our work at all, but it's going to help me with my explanation once I've got the. Okay, that looks pretty good. Now, let's do one thing at a time. This normal curve right here that I just drew on top of the data set, that is a normal curve with the mean and standard deviation of the data set. It is the one we used for our calculations in 6 and our conclusion in 7. Same curve. And the nice thing here is it's graphed right there on the same exact scale as the data. Okay, now how the normal quantile plot works is like this. Let me get a highlighter. You can see this normal curve right here, real clear to our eyeballs. Okay, imagine if I was able to grab that normal curve and just stretch it out to be a straight line and then tilt it to 45 degrees. This line here is meant to represent that normal curve now as like a reference line, okay? Now, these normalized numbers over here, 01, 02, 03, those are like on a scale with reference to that line. Let me just, what's a color that looks nice with blue, but different from blue? Orange is great, the contrasting color wheel, love it. Did you color wheel as a kid? Color wheel. I don't know what kids do now for art, but I hope they get the color wheel. But look here, if I trace this normal curve, not the normal curve, but if I just look at the histogram and focus my eyes, and I just try to get through the middle of each peak, I'm trying to be a little careful instead of the messy noodles I used to draw back in chapter 2. See that? That orange curve is meant to be the actual data distribution shape. And see how it's like also unimodal, but it's got a little skew. It doesn't quite follow the normal curve. Okay. Would you believe me if I told you that up to some nerdy math stuff, that dot pattern right there is, well, up to the nerdy stuff where it gets a little weird in the outlier world. But this little dot pattern, it goes, above the curve right there, where that's above the curve. It's down, it crosses back, kind of crosses back down to below the curve. When it gets back up around here, starts out less than you'd expect right there among the very young. See that? And so the idea of this normal quantile plot is to show us kind of how far off the data values are from where they would be in a normal distribution with one graph for all the values. So it's like those little numbers we calculated in number 6 that were all, the person I talked to who double checked their calculations with me, their values all came in a little bit below 25, 50, and 75. And when you get all the values off a little in the same direction, it's because of skewness like this. Like the below is like, because the median is like this far below the median of the normal curve. The first quartile is just a little bit below the first quartile of the normal curve. The third quartile is just a little bit below the third quartile of the normal curve. Same idea, it's a little bit off. And since there's this like lovely kind of mustache pattern to this normal quantile plot, the more smooth the pattern looks, the more it represents some kind of skewness or some other pattern that takes us from normality. You'd never expect them all to be right on the line, but the more random and the closer they are to the line, the better the normal model is for that data set. The more random and the closer to the line, the better the model is for, the better a normal model is for the data set. Here, they're not all that random, but they're dang close to the line, right? So my observation would be on number 8, something like with values mostly very near the line in the normal quantile plot, the normal model's probably an okay model for these data. They bend away, with a little bit of a pattern. That indicates the same skewness I saw back in the original histogram, or the way that all 3 of my probabilities from number 7 were just a little below my expectations. 3 ways to see the same thing here, but it turns out that they're all useful in different settings. The normal quantile plot's actually more and more useful the smaller the data set gets, because then you might not even have enough numbers to figure out if a histogram should have been a bell curve or not. But this thing will still work. You'll still see random numbers near the line if normal distribution makes sense. Kind of cool. So useful and interesting graph in some settings. We'll see it a lot more in stats 2 if you go that path. If you're not heading to stats 2, this is your one visit with the normal quantile plot. So I hope you like it and can appreciate that it's got some interesting analytical value. If you're trying to match up a probability distribution to a data set, it's a tool for that. Yeah. All right, cool. That's number 8. And hey, you're welcome for class, direct messenger. And great questions, everyone. You have asked as a group, either individually or as a group, the big questions that have confused most of the smart people who've done this work in the past. So you should have all the tools in your toolkit to work through this at your own pace. Of course, the write-up is officially due a week from today, though keep asking questions. If you have any more these next 5 minutes, I'm still here. Or if you have any questions this next week as you're wrapping up the work, especially if you didn't get a chance to talk to me or show me something confusing today, make sure to ask anytime, and I'm happy to discuss all your questions as they arise. Like, great work. Oh, and I'm going to change the due date of our normal distribution homework to a week from today for the textbook, because we really mostly talked about that today, right? So we're going to start to shift some due dates to until we catch back up with the schedule. And 2, a week from today. That's the 3rd day of March. No, the 5th day. Cool. Yeah. Of course, you got questions that are here from the video. Right, and let the folks out there know that we're, they can come in and find seats if they like.